Any second?
Yep.
Well, hello, everybody. It is time to gaze at the stars, everybody. Time for our weekly Monday morning foray into the cosmos that we call the SBAU Astro Hour. Ron Heron used to be known as the Baron. I'm sort of dropping that part right now, but SBAU stands for Santa Barbara Astronomical Unit. It's our longtime South Coast Telescope and Astrophysics Club based in Santa Barbara. I'm your host, and thank you very much. We're proud to have kicked this program off years ago on the electric radio. We meet on Zoom now, 11 to noon every Monday morning. Are we hearing me, or are we okay here?
Oh, we're hearing fine.
All right, you can watch us on YouTube, and there's 72 programs before us. This is number 73 for July 18th through the 24th, 2022. And we're going to start talking about the waning moon passing below Jupiter, where the strange new Webb telescope view of the 4 Galileo moons was posted this past week. How is the Pan-STARRS comet doing? We'll check on it. Our return to Farron Hall has been delayed. On the 5th of August, we will be online again. Our speaker is a young lady getting her doctorate in astrophysics at UCLA, Claire Williams. She's a friend of Briley's. Let's meet the gang, 4 of us on screen. Well, I'm not part of the Brain Trust, but proud to be VP, the guy that books everybody. Let's meet Jerry Wilson, president, again, running the show.
Hello.
Temporary webmaster, married to the lovely Pat Forgy, who's definitely a member and a supporter. Also married to a Pat, our merchandise manager, is Chuck McPartland, an outrageous outreach coordinator, who will get a report from moments from now. And then joining us on the bottom right of my screen anyway, married to Bonnie Murdoch, is Bruce Murdoch, who is a longtime active member.
Hello.
Now connected to us via his smartphone. He's also the president, longtime man in charge of the Santa Barbara Theater Organ Society, which also probably won't fire up without masks anytime soon, thanks to AB2 and the latest Omicron variant. I guess Tom Whittemore is out of town. What were you saying there to Bruce?
I said we did have an open console on Saturday.
Well,
There's only 6 people in the theater, so
I stand corrected. I missed that. I was out of town. Did you have a good showing?
we had 6 people. That's not unusual. You know, when it's been advertised in the paper, we get 100, but this was only advertised on our website and our hotline, our telephone line.
So the organ was brought up out of the stage at the Arlington, and it was played by whom?
Well, I played it. Gil Rosas, who's a long time.
I know who he is.
Pardon?
I know who he is. Gil Rose has been around forever.
He knows thousands of songs from memory, and he's principally a pianist, but he plays the organ very well.
Well, the only one I would like to hear really bad is Bach, the old fugue in D.
I'll play that.
Right.
I haven't played that in a long time, and I have to practice it.
I gotcha. Let's go to the outreach guide. A lot going on. Tell us what's going on in the future, and then give us a recap of this past week, seeing web pictures. Chuck?
Well, we had the special little meeting for us on Tuesday at the museum to see the web releases, and Farron was fairly full for that.
Was it?
I think a lot of people were disappointed that they weren't getting huge displays of the photographs in high resolution, because it was kind of a talking heads NASA panel that was discussing the images. So it was like looking at a Zoom screen, but they also had a display at the bottom of the pictures. And so, you know, the talking heads took up a good part of the screen. And that's kind of what they did again on Saturday. And there was a big group at the museum there to see that. And it also packed the planetarium on Sunday.
Did it really?
Because people were revved up about space. So that was pretty good.
Did they project images then on the planetarium shell?
Well, yes, I did Sunday for the planetarium shows, but not for the NASA panel, because it was another sort of Zoom meeting thing.
Well, we got Christy Cook, one of our stalwart members, as a thank for a lot of this. She did dynamite. She shared the screen in a YouTube video with a lady from, I guess, a grad student out of UCSB named Rocio. Was that her name?
No, she's a postdoc at Kavli Institute of Theoretical Physics. Yeah, Rocio Kidman. She gave us a talk too, I believe.
Well,
I'm never gone when she did it, but
I had already booked Claire Williams for August, and I suggested to her if she wanted to, start her talk with some recaps of her own impressions of the Webb photos, fine. Otherwise, she's going to talk about evolving redshift galaxies and some of the
Boy,
new theories.
That's right up the James Webb's alley.
That's right. The big five. I could only count about 3 or 4. I'm not sure about those colliding galaxies, but we'll probably talk a lot about it this hour. Mr. President, would you like to?
Really close together.
What?
There were 2 of them then, that 5 galaxies are almost they're orbiting. I think they might have been orbiting each other. They're very close together.
But the big ones are on the left, right? The 2 big ones, and then a third on the right. And where were the other 2? They were in the middle, I guess. We'll see that picture, won't we, Jerry?
Yes.
At some point, and also a strange shot of Jupiter when we get to that part.
It must have been infrared.
We try to do our weekly podcast, vlog with some funny stuff, and some of this tickles your fancy. It's President Jerry's forwarded silly science cartoons. I have 5. You can grab any one you want. The Escher mobile car that'll drive you crazy. That's
just like liking one of his where the water continuously flows downhill.
That's right. Bruce emailed cute when he was forwarded that. We got first day of school, a new better view of the galaxy, sombrero. You won't believe that shot, the sombrero galaxy. So anything you call up, we'll share with our vast viewing audience here on the Astro Hour. There it is. That's the Escher mobile car. That, oh, I'm sorry, I can't handle this. It's like those stairs that go up and down, and Escher.
They always go up.
But is it electric?
Just ignore everything in this picture except the 4 wheels. That defines what it
That's right. And don't drive it or you'll do something terrible. All right, that's great.
Yeah.
To do 2023. I'm going to buy one. You got any more?
No, I didn't arrange them in an easy manner. We'll just go right to the astronomy today.
Okay.
I'll put in the funnies for next week.
Now, I took detailed notes from your talking points, Jerry, of, let's see, the great
Square Pegasus.
Yeah, I got Pegasus, the Pan stars, the pre-dawn viewing, and Jupiter's Galilean moons. And then we're going to jump back to the last quarter of the waning moon and then Pluto in opposition. What's your pleasure? What would you like to start with, like you did in the talking points? The great square of Pegasus. It's a square northeast of 4 stars. Aquarius is a star. Okay. I should.
No, wait. No, something's wrong there.
It says 4 stars. It says so right in the.
I know, but Aquarius isn't the name of one of them.
Oh, it isn't.
No, Aquarius is a constellation.
Actually,
see Aquarius down here?
Right. Okay, gotcha. Aquarius, I misunderstood. The 4 stars are Algenib, Markab, Shayut, or a word you don't pronounce right, or Alpheratz.
Uh-huh.
The last star, Alpheratz, is part of the Andromeda constellation. Got it. The other side is Almach, 26.7 degrees east-northeast of Alpheratz. And you get calling up pictures. Where do you go with this? Gamma Andromedae? Almach.
Well, the article is
Andromeda. If we're going to do the Great Square of Pegasus, we should do that.
Yeah. Can you see the picture I've got up?
Yep.
Okay. So when I was a kid, we learned the constellations, and wherever I went in the world, camping trips out of the country, I'd look up at the night sky and it was always friendly. It was like seeing, like you're, in a sense, you're still home. Except when I went south of the equator. And I didn't think of it, but of course, all the constellations in the sky are upside down compared to what I've learned. And that surprisingly makes them very hard to find and to orient. But the Great Square of Pegasus is still a great square. And so that's the easy one to find. And then I work my way out from there. So it's shown here. And the star Almach, which has a number of spellings not shown here, but A-L-M-A-C-H is the one I use. But it's also referred to as A-L-M-A-K, Almach, is a double star. Actually, it's a triple star. And let's see if I can get the,
Monolith off the screen. I need to play.
sorry. God, got to remember to stop share first. Thank you.
Jerry, the IAU has come up with a standardized list of spellings for some of these star names, and I think the current almanac you're using is the one.
Okay.
Sounds German.
You gotta be guttural when you say it then.
So this, yeah.
Yeah, it's Arabic.
So this is, if you look at Almach, one of the four stars of the square.
Well, wait,
This is
no,
what you'll
Almach's in Andromeda.
Yeah, but it's one of the four squares.
No, it isn't.
Oh, it isn't?
It's in the legs of Andromeda.
Might be thinking of Alpheratz.
Alpheratz
Okay.
is the head of Andromeda, and that's one of the four of the square.
So Andromeda and.
But the double,
Huh.
but the one I'm showing is Almach.
Yeah, and that's in the legs of Andromeda.
Right, okay.
Okay.
And that's a double star, and it's shown here in a photograph. Very nice picture taken from Mount Lemmon. A nice orange star and a nice blue star or yellow star. And they look like they're different sizes, but of course you know that you can't resolve a star in a telescope like this. So the size effect is purely due to the brightness and how it spreads out in the telescope. They're actually, what's that?
Physically, it is also larger, but that makes it brighter, and that's why it looks bigger.
Right.
Boreal looks much the same as this too.
People should realize that they're not seeing the relative size difference.
But wouldn't the little blue star be hotter?
Yes.
Yeah.
But that doesn't mean it has more mass.
Yes, it does.
Oh, so it might be heavier. The little one might be heavier than the bigger yellow one.
Well, the bigger yellow one was probably more massive because it's evolved off the main sequence and become a red giant. But it has more surface area, even though that area is cooler, so it's giving off more light.
God, makes me
Are these
wonder.
a binary pair?
It's a triple, I think.
Yeah, it's a triple.
Oh,
So if you look closer, this is a drawing by Camille Flammarion in his 1886 catalog. And this is the blue star down here. This is the same yellow star. And at that time, there was a third, there still is, a third star. So this is a triple system. This is about 4 seconds of an arc down here, which is quite demanding for us amateurs, especially us here in Santa Barbara, because we are at sea level essentially. And 4 seconds of an arc is where you're playing with the best seeing you can get. So that's about as much as you can see. Even though your scopes theoretically will do better resolution than that, you generally don't see it. But this is a picture, this is a drawing from well over 100 years ago of the triple star system, Almach. So
And
that's
We
a
had streetlights back then to clutter up the night sky.
And
Yeah.
the image you showed, it may not be real, it may just be an artifact, but the blue star looked lumpy. So it may have been
Both
partially
stars look
resolving.
lumpy. All 3 stars look lumpy in the drawing.
Yeah.
Yeah, this is a drawing, and it may be just the texture of the paper.
No, I meant in the photograph that you showed
Oh, in
earlier.
the photo. Oh,
The
that's
blue
because I
star.
blew it up. I blew it up past its optimum resolution. So you were starting to see pixelation.
But you can see this system with a naked eye, right?
You can
As
see
a
the
single
whole
star.
system as one star. Yes.
Okay, got it.
Like,
I
it's
wonder
like
at which,
Mizar and Alcor, right?
Like the Mizar part, yeah.
Yeah.
when does science denote that two bodies circling each other, in other words, a binary system, becomes a satellite orbiting a larger planet or star? Do you follow what I'm saying? Because it would go like this as a binary, but the big part would be in the middle if it were a planet or something with planets around it. Do you follow what I'm saying?
Well, the
Those are-
orbits are more complex, but you can get a quadruple system.
It seems to me you'd reach a point if the orbiting part, the littler one, was so little it became sort of a glowing planet going around. I guess they don't call them that, so they'd be binaries regardless. I mean, do you suppose you have stars that orbit up, big stars just like planets do?
Yes.
Yeah.
Okay, but they still call them binaries.
Yeah.
Oh, okay. Interesting.
Matter of fact, to be binary, they have to be orbiting each other or a common center. What do they call it? There are apparent binaries, which are not true binaries because they're not gravitationally bound. But
Like,
true binary,
like Alberio,
Huh.
yeah.
right?
So what is that called? An apparent binary? Or
Just a
visual?
double. Yeah.
Double, okay. Yeah, that's it. It's a double star, not a binary.
Wow. So that's different. Okay. And this whole thing involves not one, not two, but three constellations, the Pegasus, the Andromeda, and the other one, Aquarius, right?
No, Aquarius is way off to the side.
Well, then why did it have the word Aquarius in his talking notes? Right at the beginning, right in front of those four stars.
There's Aquarius right there.
That's a star?
No, it's a
No.
constellation.
That's this whole thing up here.
Oh, so it's just nearby.
Matter of fact, you can see these faint blue dotted lines like there. That's the boundary of these different constellations.
Yeah, the constellation names are in color.
Yep.
In that light blue color.
Yep. And you see here Alphat's, that's
Yeah.
not actually in the constellation of Pegasus, even though it's one of the great squares or one of the great square stars. It's actually in Andromeda. And as Chuck pointed out, here's Almach, the star we saw that's a double. And in some scopes, if you have a big one and good skies, a triple.
Is,
So-
is Andromeda Galaxy part of the Andromeda constellation?
Right
Right
there is
there.
M31,
Okay.
the Andromeda Galaxy. And it's it's called the Great Nebula in Andromeda, but we just shortened it to the Andromeda Galaxy.
Got it. And right in the middle of this photograph is a large winged horse somehow, right?
Yep.
At least the front end of it.
Yeah. He's missing his rear part. And the story is when he was put into the sky, his rear half cracked off and brought forth politicians.
All back to Earth and brought forth politicians.
Okay. That's great. I love it. Thank you. Amazing stuff there, Jerry. Talking points are us. You want the pre-dawn sky viewing? You want pan stars? I keep looking at pan stars. YouTube shows me a live version of it, but I swear there's not a star around it. It's a lighter sky like daytime. I don't know if you know what I'm talking about, but I'm wondering how they show us just that little glow in the sky of pan stars, which is C27K 2017 K2, high in the southern sky at about an hour after dark. Sunset slightly brighter than magnitude 9. Sets
Actually,
near,
it's magnitude 7. It's right on the verge of naked eye. If you were in a really dark place and you had really good vision, you might be able to catch it. But that's an integrated magnitude for the entire coma, so it'd be really tough.
I think it said
Presently, pan stars. You see this star chart? Okay.
Yeah.
Okay, so pan stars is following this line. It's a straight line because I couldn't get a satisfying curve, but the actual path of pan stars goes over here. It goes above M10 and then comes down about here. So right now, pan stars is in this region here in Ophiuchus.
On Friday, it was right near M10.
Yeah.
So I tried to show it in the Malincam at the Westmont public observation, and it was just out of the field of view. So I couldn't get both M10 and the comet in it.
Okay.
And it's inbound, right?
No, well, it's outbound from us. It's still, I think, headed toward its closest point to the sun, which might be today, might be the 18th.
Yeah, I think it is. It's around now. So someone else was a little luckier than your M10 attempt. This is M10, and it's going off little nebula over there, and it's passing by over here. So that's a good shot as it passes. It's going through a rich region of the sky in Ophiuchus, and every now and then you can get it with some other object in the background or the side ground.
Ophiuchus is up there on the screen.
Chuck, can you put a focal reducer on your scope and then the Malincam on that?
That is with a focal reducer that brings it down to f3. But if I put any much more on it, it's going to really distort.
Now we can look at that picture with the tail and just by the tail and know where the sun is, don't we?
Yes, pretty much, yes.
Opposite direct. And it's not going to go within
It's-
the, it
It's
won't go in the,
approximate. It's approximate.
I'm
Well, it
sorry.
depends which tail you're looking at. The ion tail points away from the sun, but the dust tail points along the trail of the orbit.
Really?
Right, because the
So the
solar
solar wind,
the
solar
ion
wind thing.
tail away from the sun.
And that affects the dust tail a little bit. So that's why you
Right.
see it curved. Yeah.
Yeah.
But Pan-STARRS is not going to go within the orbit of Mercury, right? It's not going to go that close.
No, it's not even, it's never getting closer than the orbit of Mars, I believe.
Okay. So it's out beyond us. That's strange. It's hard to imagine that, but I guess, okay.
Well, it's really active. It was active when they discovered it, and it was out past Saturn as far as distance wise. It's coming in perpendicular to the plane of the solar system. So it's an Oort cloud object. And they think it's a first timer, and that's why it was active so early.
And so that far out, it still gets enough heat from the solar wind to cause a tail to happen, even though that's
Well,
No.
from solar radiation, yeah.
solar
Depends
radiation.
what it's made out of.
Okay.
As
If it's
far
in the-
out as, go ahead.
No, I was just going to say, if it's in the vicinity of Mars, look how cold Mars is. Why doesn't it stay cold?
Well, it is cold, but some of these ices, like carbon monoxide ice and diatomic carbon and all that, they will sublime off of it much earlier, sublimate.
Okay.
For example, take a look, remember Jupiter, not Jupiter, Pluto.
You're showing up.
Pluto has fields of solid nitrogen on the surface, and its orbit is elliptical. And at some parts of the orbit, it comes close enough to the sun, it's inside Neptune, and the sun, even at that distance, heats the nitrogen up enough and other cryogenic solids that it has an atmosphere. And then when it goes out and it's farther away, the atmosphere freezes out and they can't detect any atmosphere. So that's evidence of the sun and volatile solids.
Did the early discoverers of Pluto know all of this about its erratic orbit and
They
coming
knew
inside?
nothing. They thought it was 10 times the mass of the Earth.
Yeah.
Okay, had they known, they probably wouldn't have made it a planet. They'd have just
Right.
called it a big rock or another.
They might still have back then, but the argument for declassifying it as a major planet would have had a lot more weight.
Is that big white heart on the surface of Pluto? Is that the nitrogen you're talking about? That heart
I
shape?
believe that's, yeah,
Yeah.
You're still
among other things.
Nitrogen is an element that fascinates me. It's important for plants and it's most of what we breathe. And yet you can die underwater if you come up too fast because it becomes bubbles in your bloodstream. And my tires have had nitrogen in it for years and they've never needed anything, any pumping up. They don't go down, they don't get flat. Maybe it has nothing to do with it, but
Well, that nitrogen business in your tires is kind of superfluous because our atmosphere is 78% nitrogen as it
Yep.
stands. So if you inflate your tires with air, you're putting 78% nitrogen in them rather than 100. So it's a gimmick to charge you money.
but
Right.
does nitrogen help us any at all by breathing it in? It's the oxygen we need, right? The 20%. Wow.
There are some
Nitrogen-
nitrogen compounds that your body uses, but it's usually like nitrous oxide.
If you
Okay.
dive, if you scuba dive, and you use the standard air in your tank and you dive below, 200 feet or so, you
Okay.
get what's called nitrogen narcosis, which is where
Right.
nitrogen under pressure becomes a narcotic. And you get drunk from breathing it.
And it goes,
If you come
it
up
goes
too
in-
fast, you get bubbles and then you get aneurysm or
That's if you come up too fast, yeah, bends, you get the bends.
and it's in fertilizer, essential for growing. And at the same time, they put it in bombs to blow up the Oklahoma State building, among other
Yeah.
places. Gee willikers, that's strange. It's number 6, right? Table elements. 6 nitrogen, or I think 8 is oxygen.
8 is
Like-
oxygen.
Okay, what number is nitrogen? 6?
it's got a molecular weight of 14. So it's probably something. down around-
Nitrogen is 1 less than oxygen, so
Oh,
it's 7.
Squeaky.
interesting, fascinating. Okay, are we going to Jupiter?
Yep.
As pictured by the new Webb The Galilean moons are out there, and
Yeah.
I got to tell you, that picture that Webb gave us, I guess taken with infrared, that's how it works, was awesome and ghostly and weird and not as colorful as.
We'll get to that in just a second. This is not a James Webb picture.
Okay, got it, right.
This just shows the configuration that you're likely to run into tonight. Europa, Io, Ganymede, Callisto, and a very nice picture of the disk of Jupiter with the great red spot showing. And as you know, Jupiter rotates once every 10 hours. So 10 hours after this picture was taken, the red spot would be around here again. If you look at Jupiter visually over a period of hours, you can notice that it is rotating. And it makes it a problem to take a lot of videos and then stack the individual frames, because you have to do it so that at your resolution, the planet doesn't move very much. Also notice, if you ever try and make a drawing of it, which I did a long time ago, the planet is not circular. It's flatter at the poles and wider at the equator, because it's basically a big atmosphere and it's rotating so fast, it bulges at the waist.
Wow.
So, and if you look at it, it is noticeable.
Well, how about those bands of different colored clouds? Are they spinning in different directions, all of them?
Not in different directions, but the wind is going in different directions.
Yeah.
Well, that's the same thing.
And they're going at different speeds. So they're passing each other up and swirling and causing turbulence.
That's why you get all the eddies between them.
Right. The amazing thing to me is that the atmosphere is not uniform. It's not mixed. It's not, no matter how many times you stir that paint can, the colors won't mix.
Really? And the red spot was right in the middle of the picture recently, or supposed to be, I guess.
Yeah, well, you got a 50-50 chance of having it on one side of the planet, so you can see it.
You're right. But they saw that sucker hundreds of years ago, and that's why they say it's a 300-year-long storm at least.
Yeah, yeah.
Wow.
But it ebbs and it changes. It gets pretty muted, and then it comes back again.
About 3 times the size of the Earth, isn't it? 2 or 3 times?
Yes.
Yeah, in the 60s, the great red spot was vibrantly red. It was much different.
Well, here just a couple of 3 or 4 years ago, it was fading.
Yeah, yeah.
Really? But it came back.
It has
back.
The spot has like a 70-year color cycle where it waxes and wanes as far as how red it is. Like, it was a great flesh colored spot a couple of years ago, and now it's red again. And that just depends on when it dredges up this phosphine compound, they think, from the interior of Jupiter. And then the ultraviolet light turns that red.
Got the monolith, Jerry.
Okay.
I feel like playing Also Sprach Zarathustra. Try playing that on an organ there, Bruce.
Oh, it's
How's
fun.
that?
There we go. Do they know? Does science know what makes it happen? Why do we have a great red spot that won't go away? Why that particular part of the planet and that band?
I haven't read a rationale that I like.
Okay. But see,
So-
I'm aware of a term. I forget the term. You guys know it. Water spinning on a different direction on the north of the Earth versus the southern hemisphere, where it goes the other direction, like when you flush the toilet. What is that called?
Coriolis support.
Coriolis.
Yeah.
And that also affects our hurricanes.
Yeah.
Yeah,
But that toilet flushing is just a tall tale.
yeah.
Kidding, it doesn't do that?
No.
Well, the water in the bowl of your toilet has got jets that force it to rotate, and they can make it go any way they want.
Some do, yeah.
Well, it's all part of the cleaning action of that instrument.
Really? You've dispelled a myth. Interesting.
Okay.
Okay, gentlemen.
Well, let's get this conversation out of the toilet.
Yeah.
I was trying to be gentle there.
So this is Jupiter taken by the James Webb Space Telescope. And this is a near IR picture of it.
A near
So-
what kind of picture? Near what?
Infrared.
Near IR.
Okay, so it
Yeah,
has
yeah.
a color. All right.
So you see, in this case, you can adjust the IR pictures. So they're all false color. So this one has white as hot and dark as cool, except for this dark thing here. That's just simple overexposure, and so it blanks it out.
But there's the spot.
And,
Yeah.
and the 6 diffraction spikes off bright things is very characteristic of the James Webb, whereas on Hubble you only see 4. So.
Mhm. Now I get these spikes too sometimes on my photographs, plus this spike here because I forgot to take the mask off, the focus
Yeah.
mask. So
Did you just say the white represents hotter than the dark?
yes.
Well, then they have, Jupiter has a hot pole of the north and a south pole too, along with the,
Jupiter emits more light than it receives from the sun. It's still cooling down from its initial creation or formation. It's still generating heat from collapse and friction.
So there is nuclear fusion going on in the core?
No.
No.
Just gravitational collapse.
Yeah. It's the heating effect that if it got hot enough, it would start nuclear fusion, but it's not going to get there.
It's just adiabatic compression then.
Yeah.
Yeah.
well, something I learned recently about flights out of Guyana, where the ESA launched the Webb, is that I didn't realize this. It's obviously turning faster there. And I'm wondering if they've clocked the cloud speed in the middle of Jupiter in 10 hours, that size of a planet, how fast are those things going to make the bulge?
They're hundreds of miles an hour.
Hundreds, huh? That's
300 miles an hour for some of the stronger winds on Jupiter. Neptune has 1,200 mile an hour winds.
It's fierce.
well, I'm talking about the speed of the actual planet rotating at that place.
It rotates at different rates at different latitudes.
Okay.
Very much like the sun does.
Well, the circumference of the Earth is 24,000. What's the circumference of Jupiter? Hundreds of thousands, isn't it?
Yeah.
About 11 times.
Okay, and if you divide 10 into that, you'd get how many miles an hour? I would think.
Yeah.
Okay,
That's why it bulges out and it's not spherical.
Yeah.
the Earth does it too a little bit, right?
Yep.
The Earth has other bulges too, not just due to its rotation. It's a little lumpy.
Well, you have talking points about a pulsar. I wonder if that bulges spinning like it does.
I don't know. I don't know.
Well,
We don't know the material strength of the neutronium that it's made of.
Yeah, it is probably much more rigid, but it probably still bulges.
a little bit, yeah.
Because
So
some of them are
anyways-
rotating at a rate where they'd almost fly apart. So
What are we looking at here, Mr. President?
You're looking at nomenclature of the infrared bands. Now, this is the convention that we've always used because I worked in the infrared industry for 40 years. And down here at 0 wavelength, this is 1 micron in wavelength. And so the visible band is right about in here. And this is where the sun peaks. This is the amount of radiation that we get at the Earth's surface. And the reason there's big holes in here, for example, water here absorbs all the radiation that comes into Earth at this band. So this is the atmospheric effect of what we get on the Earth. So this is what we used to call the NIR, the near infrared, which goes from visible right there to about 1 micron, a little over 1 micron. And this is where your cameras that can sense 1 micron radiation, the Astro cameras you buy, the Malin cams and stuff, anything made out of silicon can detect weakly out to here. They drop off in quantum efficiency very much. This is called the SWIR, or short wavelength IR, is from about 1.5 to 2.5 microns. And this is where infrared shines through fiber optics to do communications. That's the primary use of this band. Then anyone want to make a comment?
No?
Yeah, the water line there at 6 microns, the military uses that to their advantage because if they want a laser rangefinder and they don't want it to be observed at a long distance away, they use, in the vicinity of 6 micron infrared.
Yeah, but it's always foggy there. Yeah, there's other military uses for this, but I'm not gonna go there. So in the 3 to 5 micron band, this is the mid-wave length. A lot of satellites look at this band. We look at the CO2 and H2O and O3 ozone layer. But we get a lot of transmission here, and this is a very common band. In order to use these bands, we have to cool the detector down to something to make it cut down its thermal noise. And in here, we can cool it with liquid nitrogen to 77 degrees Kelvin, and it works fine. These work out here at room temperature. And then the long wavelength band goes from 7.5 microns, actually 8 microns to 13 microns. This is where you and I glow like light bulbs. We peaked our black body curve at 300 Kelvin, which is our body temperature in Kelvin, peaks in this region. To get down here to look in this region, you have to cool it lower than 77 generally, frequently much lower to get way out here. But
you can put a vacuum on the liquid nitrogen and get it colder. They do that in telescopes.
yes, you can do that. It uses the nitrogen up real quick. So,
Jerry,
yes,
do these is this nomenclature near infrared, mid infrared? Is this the same nomenclature that they're using for the James Webb bands?
no, it's not, and I'm just going to show that, and because that's why I called it the old or the thing we used to use. Now, now this is the NIR cam. NIR doesn't necessarily stand for near infrared in the way that I just described it. That goes from 0.5 micron in wavelength. This is visible band out to about here. The hydrogen alpha is about 6.6 here. And so that's up in this region. So that's hydrogen. And then now we're getting out into this, what used to be called the SWIR. And then in the 3 to 5 band, this is the MWIR stuff. But they call all of this now in James W, in the James Webb, they call that near IR cam. And these are the different filters on board for different scientific reasons and to look at different spectral bands from whatever you're looking at. So these are very high performance filters, and a high performance filter is not only a high quantum efficiency here. This means that about half of what comes into this filter gets through it, but it has very sharp turn-ons and turn-offs, very steep things. The human eye has very sloping ones. It's not a high performance filter. As you get out in longer wavelength, it's hard to make the sides real steep, so they're broadened out. But with these pictures, you'll see some codes up here, which filter they use to look at it through. And then those are the wavelengths that you looked at.
Well, just for the benefit of us who don't know, how big is a micron?
A micron is, what is it, 10 to the minus 6 meters?
It's a millionth of a meter.
Yeah.
A very small part of
about
it.
100 microns. A human hair is about 100 microns in diameter.
Yeah. And the typical pixel size in your cameras that we use for amateur imaging is about on the range of 5 microns.
Yeah.
You willikers. But for some reason, the heat-seeking part of the spectrum is below our color range, and that's what infrared is, and that's how the web works. That's what you're talking about. That means you can't see heat in the other colors, orange and green and blue.
Well, it's not really heat, Ron. We perceive it as heat because it interacts with water vapor in our cells and stuff.
Right.
But it's just a wavelength of light.
Okay.
Okay.
But somehow the web turns its ghostly shot of Jupiter by adding colors so that we see it in our range.
They just pick colors that are visible to us to correspond to what certain parts of the spectrum in the infrared. And it's either to emphasize faint features that you might not otherwise see, or to bring out ones that are scientifically important. But it's really totally false. I guess you'd call it false color, but it's real data.
every single astronomy picture you see is false color in one way or another.
Well, the one picture that was published from the web, which was it was kind of like a ring nebula, but it was not M57, was
The Southern Ring.
Southern Ring, and in the middle of it they had a nice blue, sky blue color, and I was wondering, how do they do that? Because they're not sensitive there.
Yeah.
No, somebody just picked that color.
Yeah. And they
That's
pick
right.
it for both artistic and scientific reasons. And it was funny because yesterday in the planetarium, Chrissy had gotten some special effects where you could zoom in on each of the Hubble pictures on the planetarium screen. You know, you'd show first the all sky view like you'd see it if you're just standing there with your eyeballs, and then you zoomed right into the final picture. And the last one that came up was the Carina Nebula picture, and it zoomed all the way in, and then it was just a totally blank screen. So I told everybody, okay, we're showing this one in real color.
Nice guy. So anyway, you see that this is their longer wavelength camera, and it goes out to 30 microns here, sensitive 30 microns, and you see the filter on and off is not that sharp. These are very difficult to reach, and this is where you have liquid helium down at 4 degrees in order to cool the detector down, so you're not getting thermally generated current. You're just seeing the optically generated current, which you want to see. But you notice in the previous picture I just showed up there, and in this picture, each of these filter bands is shown in a certain color. And that's the color they use when they make when they get a signal in that band. That's when they add in proportion these colors. These are the agreed to colors for James WST. So if you see something very much in the red, it's probably very long wavelength. And I'm not good with my color table to know how to add these colors up and get another color, or the color circle, I think it used to be called. So as you see again, these are labeled filters, and these are labeled with Fs.
Otherwise, that's the color band on there to the left that we're seeing, isn't it?
That's the color band you will see, but it's
Yeah.
not the color band that it produced.
But the web is geared toward the red shift area, which is infrared, and therefore when it gets a cold body in space, which exoplanets sometimes are, the small rocky ones, how's it going to see anything if there's no heat being emitted from it?
You won't see anything.
It won't see a thing, will it? But it'll know it's there. It would be transiting the star, and there's a little hole in the star or a dip in the star's brightness, perhaps, and that's the only way. And that
Well,
just
these wavelengths are also emitted by things that are very cold.
Yeah. Everything that is above absolute zero is emitting some infrared or some electromagnetic radiation at some band and in some quantity. You and I, like I say, if you look in a room like us, you won't see sunlight in there. You'll see us as the light bulbs. So we're emitting at 300 degrees.
and the very, very distant galaxies, 13 billion miles away, they're not colder by emitting red. They're because they're moving away, it shifts downward.
Right.
And we have to adjust
In fact,
to that,
that
right?
light, since you're using the terms hot and cold, which aren't quite right, in effect, that light has been shifted until it is now colder. It's been stretched out so there's less energy.
Well, if we really get deep with the web, are we going to see galaxies so far away they've passed the infrared and gone into radio waves?
Yeah, we do that.
We do that now. We do it on Earth. We have
We do
arrays
That's
like
the cosmic
the-
microwave background is microwave radiation.
And so we don't get colors from the very distant galaxies or even higher than there. How do we get X-rays if they're stretched down?
We don't get X-rays from very distant galaxies.
Oh, we don't, or gamma rays, because
Right.
We get radio waves, microwaves.
Well, that's the stretching of the fabric of space-time fabric.
It's the intervening space stretching out, and that stretches the wavelengths.
Yeah. And when a wave is emitted, one wave crest is emitted, it begins traveling at a speed defined by the medium. Once it's emitted, it's completely independent of the source. So the source can make any motion it wants, but the wave is still sitting there doing its thing. And so the object may have, or the source may have moved and then emitted the second wave. And it can be too soon after the first wave or too long after the first wave, depending on the motion of the source.
Well, are they some of those distant galaxies going relative to our galaxy and our Earth, the speed of light away from us? You suppose they've reached that fast?
I don't know if any have reached, if the universe is big enough for that to have happened. I mean, now where they really are, that has happened. But we're
Yeah,
not talking about look back time for some of this.
Yeah, none that we see are doing that. But the universe is what, 90 billion light years across,
Yeah.
45 or something like that. And we can
45,
only,
think
That's
of the
because
radius,
it's
yeah.
expanded since it formed.
yeah. So they are moving faster than the speed of light. The universe is expanding faster than the speed of light. Okay, in this picture, and it'll tie back in with what we're saying. This is the top of the great square of Pegasus here. See Pegasus?
Right.
And up here, this dot right there is Stephan's quintet. 5 galaxies, 4 of which are gravitationally bound to each other, and one of which is a foreground object, I think. And then right next to it is one of my favorite galaxies, NGC 731, which is much brighter and easier to see. So, let's see.
Here we go. Webb, give us
What's
your
that?
shot here from Webb. Somebody named Stevens, I guess, found this, right? Or
Yep.
it's named after
I think Stefan.
Stefan. Okay,
Okay, this is Steve's quintet.
there it is.
Yeah, this is the one where the two are pretty close together there, Ron.
The two
Oh, I
on the
see.
right in the middle.
Right, right.
That one and that one, oh, these two, this one and this one, those are cores. And then this one and this one, these are all 4 gravitationally bound. This one could be, is in the act of actually colliding, I think. And then this one is in the foreground. So that's the 5 elements. And this is taken with the James Webb. You get the characteristic 6 or 8 diffraction spikes.
No, it's hexagonal, so it's 6.
Well, actually, it's not because of the hexagonal mirror segments, although one of the NASA talking heads said that. It's because of the 3 arms that are holding the secondary.
Oh, okay.
Yeah,
That
and there's
makes
another slight diffraction line in here. See?
Yeah.
So
Just like a Botnov mask,
yes.
which actually has more, I think, in those minor peaks.
But the Hubble is not taking a picture like this.
Sure.
Sure.
And there's a great comparison. I mean, I don't know if we have it here, but there's a great comparison where you're not seeing. I mean, this isn't zoomed in enough, but we're actually resolving individual stars in these galaxies with James Webb.
Yeah.
Whereas with Hubble, it's just a fuzz. And you don't see that glowing orange from the hydrogen gas that's being ripped out of the galaxies in the Hubble picture.
Jerry, I see the beginning of the universe again on my screen, and I'm ready to touch it.
Oh.
In fact, it's at the foot of my.
I don't know how Tom achieved that, where he could cruise on his computer. I guess he had a second computer.
Yeah. Fascinating stuff. Well, what about some of the other pictures? Now, did we learn anything we didn't know about those 5 galaxies? They're all coming together, I guess, right?
Well, we will if we haven't yet.
Yeah. A lot of this is going to take study. We're gathering tons of data, and we have to develop that data into information and then into knowledge, and then we'll know new stuff. This is NGC 7331, which is that thing that on the finder chart was right next to the Stephan's quintet. And this is the largest and brightest of another small cluster of galaxies up here called the Deerlich cluster.
Deerlich.
Deerlich.
This is Andromeda in the middle?
No, this is NGC 7331,
Okay.
which is right next to the Stephan's quintet.
Are those galaxies?
This is a Hubble. This is a picture taken at Mount Lemmon by Adam Block. Excellent processed image. So this is what you look at if your scope is too small to see the Stephan's quintet really well. you move it over and look at this, which is much brighter. This is like 8th or 9th magnitude. Of course, it's spread out over that size, but yeah.
Is Stevens Quintet up there around 11 o'clock or 11:30?
No, it's off the field of view over this way.
Okay.
But they're all part of a local group out there.
Yeah, they're all part of our super group. What is it? The Super Virgo cluster. Virgo super cluster.
Is it a spiral? I guess it is a spiral.
This is a spiral, almost edge on.
Huh.
It doesn't look like a barred spiral. It's like just a regular spiral.
And all the discernible large galaxies you're seeing there seem to be spirals. Nice barred spiral at the middle top.
Yeah, right there. Most of all, there's a nice spiral there. This one looks like it's part way between spiral and spherical.
Huh. Wow.
Okay, let me see if I can find a picture with see this. I sent you a picture of
This is coming on the screen. Ah,
see that okay?
Yep.
Okay, so these are pictures of Jupiter again, but infrared spectral bands and previous imager. This is, there's a moon out here, Phoebe, Jupiter moon, and you can see the ring around Jupiter. And this is taken with the far infrared band 323N, and it's the super cool one. And here, this is taken with these show the filters that are used for these. So if you wanted to put them together in a color picture, you'd know which colors to assign to these things. Now you see in this band, which is not as long wavelength as this band is, you can see that we see the band structure of Jupiter. And there's the
see a
great
big blot there on the 9 o'clock position.
this, the
Yeah,
black
right.
rock.
Is that what it is?
I think that's a fault. I don't think that's an
what?
actual thing. I think that's a hot pixel or a dark pixel, dead pixel.
That's where the micrometeorite hit.
Yeah. And you can see, just taking a guess at it. No, did I, I stopped, I put up on the wrong thing. Okay, let me get back.
By the way, I guess there have been 6 micrometeorite hits on the James Webb so far.
It's in a tough territory.
Yeah.
Well, it's got gravity sucks.
Yeah.
You know, no, you look at the gravity vector diagrams, and they along the orbit they're pointing into it. In other words, things get there, they get drawn in. It's really not a good place to put it.
No. Now, on this one on the right, the longer wavelength, it's much harder to make longer wavelength detectors than it is shorter wavelengths. And when we get out here at the 20 microns area, you can see there's a lot of black spots peppered all over the thing. And you can see a lot of pixel action out here. These are definitely, and I'm just guessing this, but these are definitely, see how my guesses are definite, raw images. They're not processed. And these, I believe, are dead pixels in the
Do they
thing.
use bolometers at this long wavelength?
These, I believe, they're extrinsic silicon detectors.
Okay. All right.
But they're not a thermal detector in the sense that the detector heats up and then you measure the heat of the detector. So, because those you don't need cool that much to do that kind of detection, but it's fairly weak. These are much higher performances. So these, you take multiple images of these spots or dither, and this, in processing, this will all come out. It'll look really good.
Do they use Stirling coolers or something like? I mean, they don't have a giant store of helium that they can afford to lose, right?
They have helium on board. It's projected to last for a few years, and when that's done, then they will be using just the NIR camera. They won't be using the MRI camera.
Okay, so they don't have active refrigeration to recapture the helium. Well, they
No.
can't. Helium is so small, it can sneak out of almost anything.
Yeah, it goes through. That's why it goes. That's why your balloon deflates in the living room
Yeah.
overnight. Yes, they have a limited supply of helium on board.
Well, gentlemen, I may have missed it from you, Jerry. That glowing little sun-like object to the left on the right picture, what is that again?
One of the moons of Jupiter.
That's a
Europa.
moon.
It's one of the Galilean moons. The moon.
Well, if the image to the left is any hint, it's Europa.
Okay, and it's got enough heat to.
Yeah, that's it. Yeah, it's the same thing. It's Europa.
And Phoebe is
And that-
not one of, okay.
That other black spot the big black spot there on the left, that may have been a background star that they had to kind of nuke out.
Oh.
Could be. If you look at even in expensive amateur cameras, if you look at a raw image, it's just loaded with dead pixels and stuff. But processing takes all that out, and it looks beautiful after a while. You can buy cameras. You can spend a fortune getting a scientific grade A camera, which most of us do not get. We get a B grade camera, which is good enough, because processing takes out all the crap.
Well, why is the picture of Jupiter on the right totally bright and the one on the left shows us the lines of clouds?
Different wavelengths.
Yeah, the
Yeah.
structure, you don't see the structure on the right picture that you see in shorter wavelengths.
You see the bulging of the poles too in the right picture.
Yeah,
And I now see Europa in the left, where that bright little thing is on the right. I now answered my own question. And Phoebe is not one of the four. Can you
No.
you can't normally see Phoebe in a small telescope, just those,
Right.
there's about 60 Jupiter's moons,
yeah.
79.
79.
And counting.
Yeah.
I've stopped memorizing the number in the 60s.
Yeah.
So
Any
you
number
can
you learn
recite
is a
that
lower
far up?
bound.
Yeah.
They all have
On
names.
text, you can recite 60 moons.
I can't recite them except tell you the moon number 1, moon number 2, moon number 3.
They have
Because
not
I know
all been
enough-
named yet.
Yeah,
Oh.
They have a catalog name like, J202, J200213, something like that, but they haven't given them their Greek or Latin names yet because they're trying to come up with something everybody agrees on.
And that little volcanic one, Io, is the closest in. Do any of you know how far out from Jupiter it is?
I think it's about as far out as our moon is from us, so like 240,000.
Oh, okay. That would answer a question that why isn't Mercury volcanic? But it's 30-something million miles away from our sun. And I guess it's not set up for volcanoes, but that little Io, boy, it's just wrenching, isn't it? And it's Jupiter's gravity.
And the other moons.
Well,
And
also Mercury, it turns 3 times for every 2 times it goes around the sun, or the other way
Yeah.
around.
Yeah.
So it a long time. It's very slow with respect to what face of it is to the sun. So it doesn't undergo, the pushing and the pulling of the heating and cooling on a short term, like the Earth does every day.
And it's gone past the sun on the other side. What's the status of Mercury right now? We didn't do our planets.
Mercury was
overthing.
at superior conjunction just a day or two ago. So
yeah.
But was in
It'll be back in the evening sky.
Well, gentlemen, we'll also be back on this screen in a week, maybe with Tom Whittemore, our newsletter editor, joining us. Who knows? Maybe we'll get Chrissy on board if you feel like it, sir.
Mhm.
I guess we'll terminate it here and invite everybody to, what's the next outreach, Mr. McPartland?
this Friday
Friday.
is, I think,
Kachuma.
Refugio.
Oh,
Saturday's Kachuma.
When's Westmont on a Friday?
Westmont was last Friday.
Oh, okay, I missed it. All right, and we'll have a back on screen get together with Claire Williams, a aspiring young astrophysicist at UCLA on the 5th of August.
And just a note on Chrissy, I don't think she can easily do this because of her work schedule.
Of course, I just realized she's there at the museum.
Yeah.
and The heroine of last week, I got to tell
Yeah.
you. I'm sorry I missed all that, but thank you very much for a very enlightening show. I always learn something and then I forget it in the next few days, so I got to rehash it the following Monday.
So you have to
Take
go
care.
back and play the recording, huh?
Yeah, that's right. Take care of your wives, do some wheelies with those Teslas, and Bruce, you stay healthy, okay?
Thank you. I
Good luck to
endeavor
all
to
of
do
you.
that.
Thank you, and we'll see you next week.
Okay,
Bye.
thanks, everybody.
Gotcha.
Bye
Take
now.
care. Bye-bye.